All right, let us start the presentations. Thanks for coming to these sessions. My name is Yuki Nishiwaki. I am working as a software engineer in Line Corporations, and he standing next to me is one of my colleagues, Dinesh. He is also working as a software engineer. Today, we would like to share our RabbitMQ operation experience. Before start, let me briefly explain today's sessions. Although our cloud scale gone up year by years, we haven't seriously got along with the RabbitMQ deployment and the configurations. So that way because of that, we actually experienced the several outages we could actually avoid. So that way in these sessions, we will not talk about the detailed RabbitMQ tuning and the detailed advanced RabbitMQ configurations. Instead, we would like to share with you about what kind of outage we've experienced, and also how we actually improve, and what we are thinking to make our OpenStack cluster scale more than now. So first of all, let me introduce our companies very quickly, since our company is not so famous outside of Asia. So our company Lines actually provide the messaging applications, which is similar to the Telegram or WhatsApp. And the service scale is not such as most. We are actually providing the service to the multiple different countries in the Asia. And we have right now the more than 164 million monthly active users altogether. And also, we are not just providing the messaging app. Along with the messaging app, we also provide news service, payment service, and also the music service, and so on. So that way, in Line, actually, we have several application and development teams. From the infrastructure management team point of view, we actually need to provide the private cloud service to the multiple different type of the workloads. So here is the key concept of our infrastructures. Also, we have more than 2,000 application developers within the 10 different locations. Our infrastructure management teams is actually centralized into the one organizations, and we actually are working for that. And actually, instead of rating service and application development teams that consider the detail of the infrastructure layout, infrastructure management teams is actually in charge of all of the infrastructure management. And also, as the previous slide I explained, that we actually provide the service to the multiple different countries. So that way, our private cloud also provide multiple regions. And here, actually, this slide actually explains the Line's whole infrastructure scales. Actually, this number is not including the spare servers, but still, if we look at the largest regions, we have right now the 20,000 bare metal servers, and also there are 43,000 virtual machines. Actually, these servers is not managed by just OpenStack. This red colored graph and this red number is indicating the scales, which is actually covered by the OpenStack. So as you can see here, actually there are still many servers which are managed by the other solution like VMware or manual setup. But recently, actually, we are actively working on the workload migrations from the other solution to the OpenStack cloud. So if we look at the last 1 year, we've actually created the 20,000 VMs. So that way, we actually expect to go up more and more. And here is the basic information of the Line's OpenStack. And we are actually using 7 different components, including the basic component like Nova, Neutron, Keystone, Grounds. And also, we are actually using the Troop and Designate as well, with the customizations based on the Mitaka versions. And also, the rightest block actually show you the scales that we have right now 3 different OpenStack clusters: productions, development environments, and semi-public clouds. For the production environment, we are right now managing about the 9 600 hypervisors. And for the dev environment, we have now the 600 hypervisors. And for the same public cloud, recently we started to provide. These are still experimental phase, so that's why we have just 20 hypervisors. These 3 OpenStack clusters right now are managed by the 6 OpenStack developers. Here is the very, very overview of our OpenStack deployment structures. We actually classified the OpenStack component into the 2 types of the component. One of the component type is the global component. Keystone and designate is actually classified into that global component. For the global component, logically, they don't have the multiple database, multiple deployments. Of course, from the site disaster recovery point of view, we actually deployed these components into the 2 different locations, but they are actually configured to use cross-regional replicator database. And the other type of the component is the regional component, and the Nova, Newton, Grand, Cinders will be classified into that type of the component. And for the regional component, we actually deployed the database and deployment in each regions. This is a very overview of our deployment structures. And also, if we look at the RabbitMQ deployment, here actually explain the overview of the RabbitMQ deployment. And we have 3 key points in this deployment. First one is HA configurations. We have deployed 3 RabbitMQ nodes with the HA mode all configuration so that all of the queues will be replicated with all of the RabbitMQ nodes. And also for the monitoring, we actually enabled the RabbitMQ management plugins and configure the parameters to collect the metrics from the management API. And the third point is actually came from the deployment structures. Since we haven't deployed the designate in each regions, we actually need to hold VM create notification and VM delete notifications to the regions which deploy the designate, so that designate can create the DNS record for each VMs, so that application engineer can log in to that VMs with the VM name. So this is overview of our RabbitMQ deployment structures. And with this deployment structures, we've actually experienced several outages. So from next slide, my colleague Dinesh actually will introduce what kind of outage we've actually experienced and how we actually improved.
Thank you, Nishioki-san. So this is kind of a list of outages that we faced between the 2 years. So let's talk about the first outage. As you can see, we have 3 nodes RabbitMQ cluster. All the 3 nodes have installed management plugin. And one of the node hosts the stats DB. And as you can see, all the OpenStack services and our in-house services uses these 3 nodes RabbitMQ cluster. So everything was working fine, and suddenly we saw like one of the node goes down due to out of memory. And the reason we observed was the stats DB, which uses a lot of memory on that particular node. So this was the situation. So next thing we observed, like it has blocked the client connections. Then the clients actually moved to other alive nodes, that is RabbitMQ node 1 and 2. And then the same situation could happen since the stats DB moved to RabbitMQ 2, and it could cause the out of memory for that node as well. So this was the situation we observed. And as a solution to this problem, what we actually did is we have separated the data nodes and management nodes. By data nodes, we mean that the OpenStack clients and in-house clients will use the data nodes for their normal operation. And the management nodes install the management plugin, and they will host the stats DB. And those management nodes will only be used by operation and monitoring purpose. We have also tuned the collect statistics interval from 5 seconds to 60 seconds to reduce the internal traffic. And since we actually use RabbitMQ version 3.6.5, RabbitMQ community claims that we have actually resolved this memory issue of statsdb using high memory issue on that particular node. So they have resolved that using distributed statistic collection, and that patch, that solution is available in 3.6.7. So if you use greater version than 3.6.7, you might not face this issue. Now let's talk about the next outage that we faced. As you can see, we have 3 data nodes and 2 management nodes. Now in this situation, we observed that one of the node goes down due to out of memory. Then the other 2 nodes, since the clients from RabbitMQ node 1 shifted to RabbitMQ node 2 and 3, those other 2 nodes hit the limit of socket descriptors. And then we observed like a client seems to be connected to the RabbitMQ cluster, but the RabbitMQ itself was not responding to the operations. Then we have observed like RabbitMQ internally figures out which nodes are alive and which are dead. So internally it has network partition was happened in the cluster. Then we observed like the final situation was like queues were not synced. Then multiple neutron agents and Nova computes were down, and finally the services failed to communicate. So this was a situation we observed, and as a solution to this problem, we actually increased the file descriptor limits on all the nodes from 16384 to 65536. So let's talk about the next outage. So this comes from the deployment architecture actually. So as Nishiwaki-san already explained, we have 3 regions, region 1, 2, and 3. And the global components, mainly the designate, is deployed on region 1 and 2 in the DR fashion. So the instances that we create in region 3, the record sets of those instances has to be added to the designate database, which is deployed in region 1 and 2. So we basically transfer the RabbitMQ messages from the notification designate queue to from the region 3 to region 1. So initially we were just transferring the messages from region 3 RabbitMQ cluster to just one data node, which is RabbitMQ node 1 from region 1. And as you can guess, if that node goes down, the instances created in the region 3 were not accessible. So this was the situation. So to resolve this situation, we actually started to send these messages from region 3 to all the data nodes of region 1. And here also we could face the situation and that we faced, like one of the node went down, and we observed like since we use shovel plugin of RabbitMQ to send and transfer the messages from region 3 to region 1, shovel actually has behavior of like if it doesn't find the queue on the destination node, it actually creates that queue with durability flag as true. And in our designate service, we don't use durable queues. So when the node restarted, the shovel plugin actually created that queue, the designated queue with durability true. And the designate sync service were not able to produce and consume messages from that queue, and it failed with the error with precondition failed, and it expects the queue as non-durable, but it was created as durable. So this was the situation happened due to a shovel plugin, and we actually have spec of review to resolve this situation in Oslo specs. So this says support notification transport per Oslo messaging notification. In current Oslo messaging, there is no provision like you cannot send one notification to different RabbitMQ cluster and the other notification to different RabbitMQ cluster. So this will basically, this proposes to have transport URL per notification. So these are the solutions. One is the proposed and other one is alternative. So this was about various outages that we faced. Now let's talk about the current architecture that we have. So over the period, we realized that Nova and Neutron are the biggest consumers and users of RabbitMQ. So we decided to why not prepare a dedicated RabbitMQ clusters for Nova and Neutron. So right now we have a dedicated RabbitMQ cluster which actually contains 5 different nodes, 3 data nodes and 2 management nodes. For dedicated Nova, then the similar same kind of RabbitMQ cluster we have for Neutron, and same RabbitMQ cluster we have for other services, which includes Keystone, Glance, Trove, Cinder, and Designate. So let's zoom into one of the cluster, let's say used by other services like Keystone, Glance, what policies and what configuration we have. So as you can see, we have 3 data nodes and 2 management nodes. Then we have load balancer, hardware load balancer in front of the data nodes, and all the clients actually connects to the hardware load balancer, and it then sends to the request to the data nodes. Then we have a couple of important RabbitMQ policies. We have HA mode as nodes. Since we have 3 data nodes and 2 management nodes, and the clients only connect to data nodes, we only want to have replication of queues to only data nodes. So we have this policy HA mode as nodes and HA params as only data nodes. Then we have HA sync mode as automatic. By default, the mode is manual. So that means the queues were not automatically synced. So if you set the HA sync mode as automatic, RabbitMQ itself will make sure that all the queues are synced to all the slave nodes. Then we have one more policy, queue master locator, which is set as min master. So RabbitMQ, when it receives queue creation request, it actually figures out which node has minimum masters, and then it sends the request to the node which has minimum masters if you set this policy, and it will create that node over there, and that node will be treated as master for that queue. So this actually internally reduces the traffic of queue creation. Then as you can guess, since we have data nodes and management nodes, we have on data nodes we have set RabbitMQ management agent, which will emit the monitoring data periodically. Then we have RabbitMQ management plugin installed on management nodes. And we have a socket limit set, as I have explained before, to tolerate one node failure. Yeah, so let's talk about the cross region RabbitMQ policies. As Nishiwake-san already explained, we actually needed to send the instance creation and instance delete notification from region 3 to region 1. We actually use, currently we use RabbitMQ shovel policy, which will transfer the messages from region 3 to region 1. And we have a couple of queues which we actually don't care, so we have set black hole policy for them. For example, notification designate.error, which we don't care, so we have set message TTL to just 1 and expire in 10 milliseconds. And same as for guest agent as well. So over the period, we realized that kind of Neutron agents or Trove agent, when they restart, they actually keep the fan out queues, and those queues do not have consumers. So they keep growing into the RabbitMQ cluster. So periodically we have automation script which will monitor the non-consumer queues, and periodically it will delete that. So this was about various outages and the current architecture of RabbitMQ we have. So we have a couple of backports that we have did in Mitaka version, since we use Mitaka from the Oslo messaging library. So let's talk about one important backport that we did, which is delete fan out queues on graceful shutdown. So when basically producer, for example, in this case, there is a neutron server, when it sends the message, it actually sends to the exchange, and depending on the routing key, it will be sent to the one of the queue or one or more of the queues. Then finally, it will be received by the neutron agents, the consumers. So this is the normal cycle. So you can imagine if the agent is restarted, it actually declares the queue, new queue, and the old queue remains in the RabbitMQ. And when the message is sent by the neutron server, the exchange makes sure that it sends to all the queues, and the queue that is recently created by agents, the agents consumes the queues from the recently created queue, and the other queue keeps getting the messages from the exchange. So many messages left in the RabbitMQ cluster. So upstream actually has solution to this, and the patch got merged in Newton, so we backported that to Mitaka. So what it does is actually when the neutron agent restarts or any service restarts, it makes sure that it deletes the previous queue before it creating the new queue. So no more non-consumer fan-out queues. So this was the important patch. So let's talk about the next patch, which is use default exchange for direct messaging. So when there is a RPC communication between the two services, the consumer service actually gets the message, and that message actually has the reply queue information, and it gets that reply queue information and it sends that reply over that queue. So you can imagine if the node got broken, the exchange migration sometimes does not happen, and it will not get the how it will send the message. So if the exchange is not there, so it fails to send the reply. So finally, upstream has solution to this. So it actually recommends to use default exchange, which is created by RabbitMQ broker itself at the time of beginning. So when the message sent to the default, it can guarantee that it will be received by the consumers. So this is the description, like the default exchange is the direct exchange with no name and pre-declared by the RabbitMQ broker itself. So every queue that is created is automatically bounded with that direct exchange. So there is a guaranteed message delivery. So even if the exchange goes down, RPC reply are correctly delivered. So this was about various backports that we did to our Mitaka version. So next thing is monitoring about the RabbitMQ and monitoring about the itself Oslo messaging library. So that will be explained by Nishiwaki-san.
Yeah.
Thank you.
Thank you, Dinesh. From me, let me explain the monitoring activity, especially around the RabbitMQ and also messaging. This is overview of the RabbitMQ monitoring. This slide actually just describes very common things. We actually use the RabbitMQ Prometheus exporter, which is open source implementations. By using this exporter, actually we can collect the metrics from the management APIs. And then we can actually judge if the network partitions is happened or not, and also the queue synchronization status for the each queue. And also the total count of the RabbitMQ resources, like consumer, message, connection, exchange, and so on. Actually, by using these exporters, we could easily monitor these items. And as I explained in the previous slide, actually this RabbitMQ itself monitoring can be easily done by just deploying the one Prometheus exporters. But actually, our interest is not to check if RabbitMQ works well or not. Instead, actually, we are interested in to check RPC or notifications which is delivered over the RabbitMQ works well or not. to achieve that, actually the RabbitMQ monitoring itself is not enough. So that way we actually started to think that probably we need to monitor the Oslo messaging behavior as well. Let me explain more background of this Oslo messaging library monitoring. Why we need to monitor Oslo messaging library. Probably all of the people here that have an experience to see the RPC reply timeout. Actually, initially, we actually thought every time we got RPC reply timeout, oh, probably this is because of the scale, or probably this is because of the RabbitMQ bottleneck or something. We just push all of the fault to the RabbitMQ. But actually, behind this RPC reply timeout, there are still several reasons. Like probably RabbitMQ lost the message. Probably RabbitMQ take a time to deliver a message. But probably RPC server itself can be get exceptions without replying. And also the RPC server itself took a really long time to perform RPC. Actually, the last two reasons is completely none of business of the RabbitMQ. So that way, even if we could make sure RabbitMQ works very well, this situation cannot be detected by the RabbitMQ monitoring. So that way that we actually decided to, or we probably need to monitor the Oslo messaging library itself. This is still very experimental phase and the POC phase, but let me share with you about the basic ideas. Now this slide actually show you the two type of the nodes. One is compute node, which run the Nova Compute and the Neutron agent. The node is the controller nodes, which run the Nova Conductor, Nova API, or other C-plan softwares. To monitor the Oslo messaging behavior, we actually need to apply the patches into the Oslo messaging library, which is actually deployed into all of the type of the nodes. And the dispatch actually export internal state of the Oslo messaging to the Unix socket, which is listened by the other softwares, which is actually named as Oslo metrics. We actually named, and we are currently developing. And this Oslo metrics is actually in charge of collecting all of the metrics informations on this host, and then export that information to the Prometheus. Here is list. Right now we support as a metrics, and right now we just support the RPC server and RPC client metrics, and we actually implemented the 4 type of the metrics for each. The total count of the RPC exceptions, and also total count of the RPC starts, total count of the RPC finish, and the processing times. Actually, by making use of the total count of the start and the finish, we can actually calculate how many RPC is underperforming. And also, if we just make use of the RPC start count, we can actually calculate how many RPC is actually executed per second per minute. This is samples from one of the metrics, which is the RPC server invocation start count total. This is actually represent the RPC start count. These metrics have the 7 different fields. The first 4 fields is about RPC servers, and the last 3 fields is about the messaging bus related informations. From top, endpoint is actually representing the RPC server class, and the method is representing the RPC server's method. And also namespace and version is also about RPC server's class. And this sample is actually collected from the Nova Conductor. So that's why the endpoint here describe conductor managers, and the method is object class actions versions. And the last 3 fields is like the exchange and server and topic. This is all about like the which exchange, which topic this RPC server is bounded. And the last value is the 155 value is actually indicating how many this conductor managers object class action versions method is evaluated. In these examples, we can see like conductor managers object class actions versions is evaluated 155 times. As you can imagine from these samples, actually this metrics activity is also help us understand how exactly OpenStack process communicate each others under the pressures and in the such a large scale. So this is actually the last slide of today's sessions. So far we've explained what kind of outage we've experienced, and also how we actually improved, and what is the current RabbitMQ deployment architectures. And then we also introduced monitoring activity, including the POC of the Oslo messaging library behaviors. So in this slide, actually, I would like to explain what we will work on in the next 1 year and 2 years. The first things we will do is making the Oslo messaging library monitoring production ready, and we deployed that monitoring into all of the production environment. And then actually we are planning to perform the benchmark emulations with the monitoring. After we introduce also messaging library monitoring, that we could actually observe which RPC method is frequently evaluated, and which RPC method is taking more times. Based on that, we are thinking to perform the RPC tuning. And the last topic is RabbitMQ disaster testing. This is similar to the benchmark emulation, but we are also thinking to perform RabbitMQ disaster testing after we introduce also messaging library behavior monitoring to understand if RabbitMQ node goes down, how exactly RPC implementation got affected. In the next summit, I hope we can update this topic. This is all we've prepared today, so thank you so much. Any question? We would like to upgrade Mitaka to the Newton or latest versions, but right now we are actually preparing.
Thank you. Do you plan to contribute Oslo metrics exposure or something?
Yes, we are thinking to contribute the Oslo metrics once we are ready to publish. We are currently preparing.
Okay.
Yeah.
I'll wait. Yeah.
Thank you for your sharing. I have one question. Is about that you say that when RabbitMQ have problem, it is almost caused by memory used up.
Right.
And can you share some detail about in which situation memory is used up, and do you have any problem about partition, the RabbitMQ partition, and can you share something about this? The RabbitMQ partition and memory used up, these two, can you share something about this?
Memory. So the first thing we saw is the out of memory issue was related to statsdb using a lot of memory of that node. This was the first outage that we saw. Probably it's so that is one reason. And the other reason we have experienced is related to one node getting lot of connections from the OpenStack clients. So all the clients connected to just one node.
Yeah.
So it could cause the RabbitMQ, the out of memory issue. Yeah, so this was the situation of statsdb using a lot of memory of that node. And the other situation was this particular node was getting a lot of traffic, lot of connections from the clients.
So there are a lot of messages not consumed in the RabbitMQ, you mean?
No, I mean since this is a three data nodes cluster, all the clients got connected to just one node,
Yeah.
And this particular node was serving the traffic, just this node, and it can cause the out of memory issue for that node. So the other two nodes were not getting any traffic.
Okay.
Yeah. So that was the situation. Yeah.
Well, first of all, great presentation. Thanks so much. I kind of like heard that you say that the load balancer was a physical load balancer. So I was wondering if you have HA for that load balancer, how it works. And also, seems like you have hosts for all these RabbitMQs. Are there all physical machines running behind them? Or how do you orchestrate all the RabbitMQs that you're deploying?
For the first question about the HA configuration for the load balancer itself, you meant? Actually, I'm not so sure about that part. Since actually the other teams is managing for this load balancer, but we are actually probably implementing the BGP based, like the routing based. The anycast by making use of the anycast IPs, we are actually having the multiple load balancer, I think, and also for the RabbitMQ deployment, we are actually using the bare metal servers. How many cores?
Physical machines you're using for all the
Rabbit? Just 5.
3 clusters. So
yeah.
3 clusters have 5 nodes in each.
Yeah.
3 are data nodes and 2 are management nodes.
How
so
big
like
are your servers?
The I think 64 gigabyte memories, and for the number of core would be the 32.
Yeah, 32.
Yeah.
Thank you. You did not mention anything about the auto-heal mechanism you used in RabbitConfig. Auto-heal, it's a configuration in the Rabbit. It can be either, if I'm correct, it can be either pause minority and or I don't remember the name of the second one, but something like that. Do you know which one you have?
We actually have just ignore the default one.
The default one.
Yeah.
So it may not be pause minority.
Yes.
It's the other one.
Yeah. So it's I mean the default one. So we actually don't want RabbitMQ itself to recover. We want to monitor the situation and we want to check the state of the RabbitMQ itself and then decide what we should do.
So you never checked pause minority, because I remember that we had a talk a few years ago, and it seems that pause minority is maybe a little bit more efficient when we have a splitting of the cluster.
Okay.
It's not something you checked, right?
We checked, but we didn't pay attention to that since we want to basically have a state of monitor the state of the RabbitMQ before it actually makes heal by itself.
Okay, thanks.
Yeah, thank you.
So the question is, so every time when there is a network partition happens in the RabbitMQ, we end up restarting all the API. Okay, so we are using the container-based OpenStack environment. So every time we had to restart all the APIs on all the control nodes, it even includes on the computes also, compute agent and compute services. So this Oslo messaging, will it of any help, or is there any other things we have to check to narrow down this issue?
Yeah, actually, you don't need to restart the API service. Actually, Oslo messaging has retry logic. It will keep reconnecting to the nodes. If you fix your RabbitMQ cluster, clients will automatically connect. Oslo messaging has that retry logic.
Okay, so but for some reason it doesn't work like that. So even though the network partition recovers, the APIs doesn't, as a consumers, they don't use them. It's not able to connect.
It's not able to connect, you said?
Yeah.
Actually, there we haven't observed that situation, but we actually have similar situation like this. If network partition is happened and just recovers, actually that operation is not covering each queue's status. So that way there, after you recovers, if some of the queue is still left as an unsynchronized queue, actually there's API and other like the agent and conductors communication sometimes fails. So that is actually, if we that way there's, when we face that situations, options we can take is the restart all of the process or like this, make sure all of the queue has been synchronized. I'm not sure the solutions will work for your case, but we actually have similar situations before.
Yeah, thank you.
You can make use of HASync mode.
Yeah, and also if you actually configure the HASync mode as automatic, actually that queue synchronization stuff will be automatically done by the RabbitMQ side.
Yeah, thank you.
Thank you. So, so for the region 1, I see you have about 5,500 servers, and so it's supported by 5 RabbitMQ nodes, right?
Actually, it's a bit different. So for the bare metal server, actually we are not using the RabbitMQ and OpenStack at all. Actually, we have kind of the ironic, like the software we developed.
Okay, you have ironic nodes in the 5,500 nodes there, right?
Kind of, but that software actually is not using the RabbitMQ at all. So that way, this RabbitMQ is only used by the Nova and just Nova.
Oh, you know, so for the 5 RabbitMQ nodes, just use it for Nova?
More like for the OpenStack component,
okay.
but in terms of the computing service, we just use the Nova. For the Ironic, actually, we use kind of other solutions.
Okay, so what's the kind of hardware configuration for all these RabbitMQ nodes? It's like the how the memory, what's the size of the memory or something like that?
Yeah, we actually use 64 gigabyte memory and 32 core.
Only 64?
Yeah.
Not large. Okay, so since you update the RabbitMQ from 3.65 to 3.67, is there any other problems that you have met? Do you have any other problems?
Related to RabbitMQ version, you meant to say?
I mean, since you updated the version of the RabbitMQ,
we actually haven't updated the version.
Right.
We have versions 3.6.5, and RabbitMQ community actually claims that they have resolved the memory issue in 3.6.7. We will basically upgrade, but right now the cluster is of 3.6.5.
Okay, thank you. Okay, thank you very much.
Yeah, maybe time is up. So thank you for listening.
Thank you so much.